Yeah. So, so the best examples are platinum and gold. Now, apart from platinum and gold, there are some metals which also give this passivity behavior, that is the lack of activity or lose of chemical reactivity under certain conditions. And what is the mechanism here? You just look at here the mechanism. See, this is the metal which we have. So what will happen is, in this metal, under certain conditions, it will form an oxide layer. On top of the metal, definitely there will be an oxide layer formed, which will prevent the further oxygen to come to the surface of the metal. And this oxide layer, because it is acting as a barrier for not to allow the oxygen to reach the surface in order to extract the electrons. So this oxide layer is almost like an inhibiting layer. So it stops preventing the further oxygen to react. So what will happen? Obviously, your corrosion will not go. Is it not? See, for the corrosion to take place, what are the primary things we discussed in the mechanism? The iron mechanism, what are the primary things we want? We want water molecules, we want oxygen, we want electrons. We are discussing. So if you miss any one of them, again there won't be any further reaction as I discussed. So we have showed also, I have given some 4 cases. In a similar way, for any corrosion to took place, the main species is oxygen. Oxygen has to interact with the surface. Fine. So, for example, if this is my surface, if let us say there is an oxide layer formed on the surface, what will happen? This oxide layer will be an inhibiting layer for further oxygen to react to the surface. Yeah. So, if there is no oxide layer, oxygen directly react with the surface and can extract the electrons and do whatever the phenomena for the corrosion to take place. So, this oxide layer, if this is the metal, oxide layer will be MO, metal oxide. Is it not? That's what I given some examples of this gas cylinder catching the fire. What we do, we will cover with some wet blanket. So this wet blanket is stopping the oxygen to react with the fire, because oxygen is an oxidizing agent. So it enhances the fire which has caused. So I am stopping the oxygen to further react. In similar way, if this is my metal, this oxide layer is formed on the surface will stop penetrating the oxygen to react to the surface. Fine. So the formation of oxide layer will lead to passivity. Otherwise, it is active. See, if there is no oxide layer, this metal is very active. It will lose electrons. It will undergo corrosion. But if any oxide layer has formed, this will become passive, because this oxide layer is not permitting for the further oxygen to react, because this much of thickness oxide layer has formed. The best example is solar cells. So, what is the main principle involved in solar cells? Silicon solar cells. You have seen why Narendra Modi has become very famous in very short time, because he has implemented these solar cells in complete Ahmedabad. You go around Ahmedabad, wherever you go, even in streets, lakes, parks, he has implemented this solar cell business. So, what is solar cell? It extracts the sunlight energy, which is free of cost, converts to electrical energy. So, free source to the our electrical energy conversion. So, no need of pay the electricity bill. If you have just fabricated a solar cell, put on your house tops, you will get free current. So he has put up this solar cell technology in an entire Ahmedabad city. So very soon he becomes CM and then he becomes PM. Now in the second term he is leading the country. So what is the necessity of silicon there? See, solar cell is very important for the material called silicon. Fine, that's why it is called silicon solar cells. So silicon is a semiconductor which absorbs the photons, forms electron hole pairs, and then converts the electrical energy, whichever form we want. There is another ways we conversion. Let us leave it about it. But the main problem with silicon is it quickly forms a silicon oxide. Silicon, if you look at your silicon, the coordination number is 4. So silicon is coordinated with four oxygen bonds: top, down, left, and right. Now, if you talk about silicon on the surface, the top bond is dangling bond. So there won't be any oxygen pair because this is the top only. Top surface means there are no bonds to oxygen. In the bulk, if you consider, oxygens will be attached to silicon. But when the top bonds are free, silicon always wants to pair up with the oxygen. Because in the atmosphere there are plenty molecules of oxygen, oxygen will be quickly taken by the silicon. So if oxygen is quickly taken by silicon means Si react with oxygen to form SiO2. So an oxide layer has formed. So when silicon, an oxide layer has formed on the surface, it will become insulator rather than a conductor. So if it becomes an insulator, where is your electricity passes or conversion of electrical energy? Fine. So that is why silicon solar cells will work only if silicon is there on the surface. But it is highly difficult to make silicon to be act only silicon because silicon quickly react with oxygen to form an oxide layer of silicon dioxide. We call as SiO2, silica we call it. Silicon is Si, silica is called SiO2. So this oxide layer is an insulating layer. This oxide layer formed is an insulating layer. So there won't be an electron pass, there won't be further oxygen to get into the surface of the metal. So your complete silicon solar technology will be gone. That's why if you remember the silicon solar cells, the fabrication costs are very very high. They do the fabrication in inert atmospheres. There is a separate room where even small air molecules cannot enter into the rooms. That is why the solar cell fabrications are very cost, and that's why the initial investment cost is very high. Why poor people cannot afford solar cells in our home? Because the initial investment is very cost. A small panel of silicon solar cell costs in thousands, 50,000, 60,000. A small, maybe a 4 meter to 4 meter is around some 50 to 60,000. So no, who will afford? Because why they put that much amount is because of the cost involved in fabrication of the cell. The fabrication involved in clean room environments. So where they do in inert atmospheres. So the reason behind is silicon should not undergo oxidation to form silicon oxide. If it forms silicon oxide, the silicon oxide is an inert layer. Inert layer. So it will not passes the electrons to out. Okay. So that is why I given the example. So see silicon. Now first and foremost example is the silicon. Silicon, and then aluminium, and then of course stainless steel. Why I mentioned stainless steel? Because what is stainless steel? Chromium doped in iron. So this chromium will form a chromium oxide layer. So that oxide layer will be resisting for further corrosion. So that's why stainless steel will be passive. Otherwise, what will happen if there is no chromium? What is there in stainless steel? Iron only. Iron is very active. It will undergo corrosion. But added chromium in the iron, which we call as stainless steel, will form some chromium oxide layer, which is an inert layer. So there won't be corrosion. So that is the reason why materials will behave passive because of the this oxide layer. Got now? Why materials will behave show passivity or why resist corrosion is showing tendency of passivity. That is losing the chemical reactivity. They won't undergo reaction because this layer completely blocking the foreign species to enter or react on the surface. Understood now? What is passivity? The best examples are silicon. So silicon oxide, oxide layer, aluminum oxide, highly inert layer. That's why we use aluminum foils for food packets. Why aluminum food packets? We'll go to railway station or wherever maybe the packets are packed with aluminum foil. Why? Why? Why aluminum foil only used for food packing? Because aluminum will form aluminum oxide layer. It's a complete transparent oxide layer will be formed. So this oxide layer will not allow foreign bacteria to react onto the surface. So there won't be any material deterioration, there won't be any bacteria contamination, the food will be safe. So silicon, aluminum, steel, nickel. So the main reason or mechanism for materials to show passivity is the formation of the oxide layer, MO layer. Now look at here, another concept here involved. See, if this is the metal and slowly some oxide layer has developed, let us assume. Now before forming the oxide layer, what is on the surface? Now the surface metal will lose electrons. See, M will undergo M2 plus 2 electrons, that we know. Fine. Let us assume for time being there is no oxide layer. Now where this M2 plus will go? Metal will lose 2 electrons to form M2 plus. Let us say zinc will lose zinc 2 plus 2 electrons. Where this zinc 2 plus will go? Into aqueous solution. Fine. Where will electron go? Electron will reside on the surface. We understood. See, that's why the metal will undergo the surface charge will be negative. Because electrons cannot pass in the solution. In the solution only ions can pass. We know that. We know that electrons movement will be on the metals only. Ionic movements will be on the solution only. So electron cannot move in the water, in the aqueous solution. So electrons will be residing on the surface of the metal. Ions will be go into the solution. So whenever there is no oxide layer, this M2 plus will go into solution. Electrons will be residing on the surface. Now you understand here. M2 plus will go into solution and electrons which are on the surface looking for the ions to react. Is it not? Whenever H plus ion is there, this electron will be taken to the H plus to form H2. We discussed yesterday, the polarization concept. So electrons are residing and M2 plus wants to go into solution. Now let us assume oxide layer is formed now. So if oxide layer is formed, that means what? Outside this there is a gas called oxygen, and this O2 which is outside wants to take the electrons on the surface to form O2 minus. Because we know oxygen is a good oxidizer, good oxidizing agent. Oxygen is a good oxidizer. So it wants to pull up the electrons. That's why it's an oxidizing agent. So oxygen wants to pull up the electrons from the surface to form O2 minus. Now, if you see this O2 minus formed, M2 plus formed, they again have an interaction if an oxide layer is formed. So M2 plus wants to go into solution, O2 minus formed will want to go inside the metal surface. That means what? If you look at here, the oxide films which is formed will act as a conductor, will act as an electrolyte. Because see, this oxygen is completely in the electrolyte solution. Is it not? Yesterday we have discussed in the concepts. When a metal is dipped in the solution, at the interface, there will be ionic charges. So if surface is negative, positive ions will come into picture. So the ions will try to go into the solution and electrons will try to be on the surface. So if there is an oxide layer is formed, M2 plus will want to go into the solution and O2 minus, because oxygen is available, which will take the electrons on the surface to form O2 minus, it also wants to go inside, attack the surface. So this oxide layer will behave like a conductor as well as an electrolyte because it is dipped in the solution. So the film formed is also dipped in the solution. Why I said it's act as an electrolyte? What do you mean by electrolyte? Electrolyte in the sense which will facilitate the ionic movements. Is it not this is ion? O2 minus. O2 minus is an ion only because oxygen is a gas molecule. But oxygen takes the electrons from the surface to form O2 minus, ionic state. So when ions are, this film is making ion to percolate means what? It's a conductor, electrolyte. So the meaning here is this oxide layers formed act as an electrolyte as well as the oxide layers formed will be acting as a conductor. Okay. So that's what I have written here. the oxide scale or film act as both electrolyte and electron conductor. Fine. So look at here. This is, you might know that. What is this? What is this? What is this? The iron pillar. The iron pillar, which is located in New Delhi. Very famous iron pillar. People use it to, whenever people go to Delhi, they visit this iron pillar. See, the importance of this iron pillar is this entire structure is made up of iron only. Entire structure is made up of iron only, and it is exposed to atmosphere. If you see, this pillar is exposed to atmosphere. There is no top layer. There is no barricades. So rain will fall, sun will attack, foreign dust will attack. But still, this iron pillar is iron pillar. 2000 years old iron pillar is as it is. The reason behind is because I am saying this complete pillar is made up of iron. But we are discussing iron will corrode. Why this iron pillar has not corrode? Why iron pillar is not corrode? What we are discussing till now? Just now what we discussed? Passivity. We discussed till now passivity. That means there are some metals, there will be an oxide layer formed which is acting as an inhibiting layer for further oxygen to attack. So, along with iron, people at that time they have added small percentage of other elements like bell metal, phosphorus, lead, some brass. Very small percentage. If you look at the percentage, see 0.17 percentage, 0.6%, one very small percentage of foreign species along with iron, making the iron not to corrode by forming a thin surface oxide layer. So that is the reason till date this iron pillar is iron pillar only without any corrosion. You can touch the surface, very smooth surface. There won't be any scraps. Whenever you have time to go to Delhi, you just visit this place, and people are there. I think, yeah. See, this is a place where it's almost like there are 4 to 6 museums are there in Delhi, and this is one of the place where tourists will often go and see the places. And this pillar, such a great idea. You see the height of this woman and see the height of this pillar. So people at that time, knowingly or unknowingly, added small percentage of foreign elements. Don't know. See, at that time, see, I'm talking about 2000 years back. How people know that adding these will make the iron to not to corrode? If that is the case, why that much of damage we have seen in the first slides? Biggest disasters in the world. Ship sink, Mexico, USA, Canada. Fine. Why that much has happened? That also materials are iron only. If this is not corroding, that ship should not also corrode. What makes is the small percentage of composition of elements that are added acting as a transparent oxide layer, stopping the oxygen to react to the surface. So that's why this entire structure is free of corrosion, like what we have seen yesterday, the Liberty statue in USA. So the Liberty statue is still under active in the sense the design. Fine. The concept of surface areas. Copper outside, iron inside. Okay. Fine. Now, now look at the different parameters that are affecting the corrosion. Now the first parameter, effect of oxygen and oxidizers. Now let us discuss for some time. Will oxidizers increase the corrosion rates or not? Will oxidizers increase the corrosion rate or not? Of course, we have studied. We have studied oxidizing. What do you mean by oxidizing agent? A species which accepts the electrons, a species which extracts the electrons, quickly take the electrons. If any metal, if any species quickly taking electrons means what? The other one should give tendency to lose. Is it not? See, if I am giving the amount means what? If there is some person who is taking money means definitely I have to give only because this person is already there to take the money. If the person is not there, I can stop giving the money. But still, always the person is there means I have to give because he is taking all the time. So, if any species is there which is accepting the electrons quickly, taking the electrons quickly means I have to lose electrons. So, in case of oxidizing agent, the metals will lose electrons, metal will undergo corrosion fastly. Is it not? So, the oxidizing agent role is accept the electrons quickly. So, increase the reaction rates. So, if I put some oxidizing agents, so oxidizing agents will always increase the corrosion rate. So corrosion rate on the x-axis, the corrosion rate will increase if I put oxidizing agents. Understood? Figure number 1. Now you look at the scale of the corrosion rate. So what is the scale? We start with 1, 10, 100, 1000, 10,000. What is the scale? Almost like log scales. What is log scales? Normal plots, log plots. So exponential increases. Exponential increase. See the corrosion rate when small oxygen concentration is increased. See initially 1, it becomes 10. A small increase. If some more percentage of oxygen agent increase, you look at the value, it reaches to 100. And again, some more value of oxygen increase, you look at the value, it becomes 1000. See, I have not increased that much of oxygen core. I have not gone till here. Just only small fractions I have gone. The values are 10,000. That's why oxidizing agents are highly powerful. That's why we always fabricate or always plan the industries not at the seashores, because near the seashores highly oxidizing agents are available. Chlorine minus, highly oxidizing agent, oxygen, highly oxidizing agent, fluorine, iodine. So these are all highly oxidizing agents. If small percentage of oxidizing agent is there, look at the corrosion rates. Understood now? That is why see when the gas pipe catching fire, quickly we have to cover with the wet blanket. Otherwise, what will happen? Complete blast. So that quickly means I am stopping the oxygen. Otherwise, what will happen? This oxygen is enhancing the corrosion rates. See, small percentage of oxygen agent enhancing the corrosion rates like hundreds, thousands, 10,000s. Understood now? So, what is effect of oxygen or oxidizing agent? It increases the corrosion rates enormously. Here. Now, let us come back to the second graph. What is this second graph? Again, oxidizing agent only. But look at the graph of the corrosion rate. Observe the corrosion rate. For some part, the corrosion rate has increased. At certain corrosion rate, it has stopped to increase. It becomes stagnant. So that means there is no corrosion rate after that. So that is the highest value reached and it becomes stagnant. Then the corrosion rate starts to increase. So what is this tendency? The previous concept. What we discussed in the previous concept? Passivity. See, sometimes some metals will be active. But what will happen? After some time it may be become passive. That means after some time the oxide layer has formed. If oxide layer has formed means what? There won't be any further corrosion. That's why it is stagnant. It's constant value only. Corrosion rate is constant. There is no increase in the corrosion rate. It becomes constant value around some 10 or 5 or 6. Then after that what will happen? Maybe the corrosion rate increased. Why corrosion rate again increased? See, whatever the oxide layer has formed, it may be peel off. We don't know. If the air velocity is so large, the surface layer can be peeled off. What we are seeing in inside homes? We usually stop corrosion, we put some paints. But if the paint layer has broken, what again happened? Again corrosion, surface corrosion. So this oxide layer which has formed on top of the surface, if the surface has been peeled off due to high velocities or humidity or whatever the conditions, when oxide layer is peeled off means again corrosion will take place. So the corrosion rate will increase. So the first one is the active, that's why increasing. The next one will be passive, there won't be increase, stagnant value. Then lastly transpassive. So after becoming stagnant again it slightly increase. So transpassive. Active, passive, transpassive. So there are some metals which behave this type of trend. Some metals only increasing trend, no doubt. So they won't show passive. But some metal will show some active, suddenly a film will be formed, it's, so the corrosion rate will be constant, that's called passive mode, then it undergo active passive tendency. Okay, I'll give you some more examples also. Now you look at here, I'm increasing the oxidizers, I'm adding the oxidizers. For a particular cases, I'm adding the oxidizers. I want to observe the corrosion rates. What could be? So we know when oxidase is there, the corrosion rate will increase. You look at the trend. Corrosion rate is increased. Fine. Let us say, for example, for some metals, after some time, it may become passive. Then what will happen? Suddenly the corrosion rate will be constant. There won't be any increase or decrease. It will be stagnant. But suddenly, if the oxide layer has been peeled off, the corrosion rate will again increase. So you look at, there are three sections I have. Three sections, 1, 2 and 3. See, look at the example for section 1. Monal in HCl plus oxygen. I have added the oxidizer. So in case of oxidizer, monal element in HCl solution will always show the increasing trend of corrosion rates. Similarly, one more example, copper in sulfuric acid, iron in water. If I add oxidizers like oxygen, they always show tendency 1. That means they always increase, always increase. Now look at 1 and 2 sections. What is 1 and 2 sections? 1 and 2 sections means increase and then come back, make a stagnant. It's called 1 and 2 sections. So which type of metals will show both active, passive? Example is chromium nickel in sulfuric acid. If I add Fe3 plus, Fe3 plus is also an oxidizer. If I add Fe3 plus or Cu2 plus in certain chromium or titanium metals, they will show 1 and 2. What do you mean by 1 and 2? Increase and then become stagnant. That means active, passive. Active, passive. So this is the example for active, passive group. Now look at only 2. Only 2 means what? Only passive. What is the example for passive? Chromium nickel in nitric acid. If I take chromium nickel, if I put in nitric acid, it will not undergo any sort of oxidations. Passive in nature. That means what? Chromium nickel will form a thick oxide layer. There will not be any corrosion. So one more example for 2. Now for 2, 3. That means 2 means passive, 3 means transpassive. That means initially it has to show passive nature, then active nature. That's called transpassive. So what is the example for 2 and 3? 2, 3 sections. Chromium in nitric acid, if I add chromic acid. Chromium nickel in nitric acid, if I add chromic acid, it will show first passive, then transpassive. And lastly, 1, 2, 3. That means there are some materials which show active, passive, and then transpassive. That is 1, 2, 3. Active, passive, and then transpassive. What is the example for 1, 2, 3? Chromium nickel in concentrated sulfuric acid, nitric acid mixers. So why will come to know all these things? Because this all will we should know. Actually, my interest is to make you to go to Bellary where we will see all these things. Where iron steel, they completely red hot iron steel they will take, they will expose it to different acid environments. So this iron nickel or chromium nickel in sulfuric acid, nitric acid mixers, they show this tendency. Active, passive and then transpassive. Understood the graph? What is section 1? What is section 2? What is section 3? Then what is section 1, 2, 2, 3, 1, 2, 3? What is 2, 3 section? What is 2, 3 section? Passive, transpassive. So there are only few metals. Examples are see only few metals. Chromium, nickel, in nitric acid. When I add chromic acid, it will first show passive. That means there is no corrosion. But slowly after some time, it undergoes transpassive. That means what? This chromium oxide layer will be slowly peel off, slowly dissolved in the chromic acid solution. Oxide layer will be dissolved. Then dissolved means what? Again corrosion. So passive mode, transpassive mode. Clear? Understood? Effect of velocity. So sometimes the increase in the velocities will also increase the corrosion rates. Is it? Yes. See, case of example A, the corrosion rate is increased. But after some time what will happen? Because of the increase in velocity, if the oxide layer, if it is there, it will be removed. If it is removed, again it undergo corrosion. See the case of example C is, see I will show you the case of example C. You see the corrosive. What is corrosive? Lead in sulfuric acid. Lead in sulfuric acid, initially the oxide layer will be there, lead oxide layer will be there, which is passive. See, that's why there is no corrosion rate increase, passive, stagnant. But slowly what will happen, this lead sulfate will dissolve. So it undergo transpassive. So corrosive is passive transpassive mode. Fine. Now what is curve? Increasing the corrosion rates. Item sources. So curve A, what is the curve A example? See, for 1, section 1, iron in water plus oxygen. We have discussed this case. So for the case 1, even if you increase the velocities, the corrosion rates will be increased. Now look at the case B. What is case B? I have written here. You see, if you remember here, see, for corrosion processes that are controlled by activation polarization, agitation and velocity have no effect. We discussed yesterday. What is activation polarization? What is concentration polarization? What is activation polarization? Activation polarization, concentration polarization. We have discussed. At length we have discussed. Complete 1 hour. Activation polarization. 4 limiting steps. So in that 4 limiting, what are the 4 limiting steps? Bulk diffusion, reaction on the surface, chemical reaction, and then surface desorption. For surface desorption, 4 limiting steps in the activation polarization. That is at the electrode-electrode interface. What are the changes? That is called polarization. In that activation polarization, if I put agitation, will there be any effect? I told you yesterday, only when concentration polarization comes into picture, only when diffusion comes into picture, increasing agitation or velocities will play the role. See here, whenever activation polarization is there, agitation does not have any effect. Agitation or velocity, what will happen if I increase the velocities? Nothing will happen if it is in the activation polarization mode. So look at case B here. Is the case B I written here? Let's look at, yeah, curve B. This is what the curve B are written here. For corrosion processes are controlled by activation polarization, agitation and velocity have no effect on the corrosion rate as shown in curve B. Which is the curve B? There is no corrosion increase because even though I am increasing the velocities, that is under activation polarization mode, it will not affect. So there is a stagnant. Suppose if it is in concentration polarization, then Effect of velocity comes into picture. We discussed in the consonance portion what will happen if I increase the agitation speeds. What will happen? Turbulence will be generated. It will pushes the ions towards the surface. So your rates, mass transfer rate as well as corrosion rates will increase. So effect of velocity will only be having in the concentration population, not in the accretion population. So that's what we have given. So similarly for corrosive, you see I have given what is the corrosive example? Chromium, I think. Yeah, lead in sulfuric acid. Similarly, iron in sulfuric acid. Initially, initially, even if I increase the velocity, the corrosion rates will not be there. It's like a passive. Then it will undergo transpassive mode. So why it will undergo transpassive mode? After some time, the much increase in the velocity will try to peel off the surface because the velocities are so high. Formed oxide layer will be removed. If it is removed, means what? Again undergo corrosion. Okay. Yeah. Effect of temperature. So what will be the effect of temperature? If I increase the temperature, corrosion rate will be higher. See, what we studied in the CRE, what is the effect of temperature in reaction kinetics? What is Arrhenius law? The temperature dependence of reaction rate given by Arrhenius. The K equal K naught e power minus e by RT exponentially increases if just 1 degree rise in temperature doubles the reaction rate we have discussed. So why the temperature increase the rates? See, that rate may be chemical reaction rate or electrochemical reaction rate, whatever it may be. Increasing the temperature will increase the reaction rates. Why? Why? Because increasing temperature will increase the number of effective collisions. Effective number of collisions, effective number of reactions. This will increase. If this will increase, what will happen? The reaction will increase. So, if you increase the temperature, the corrosion rates will be higher always. The corrosion rate will be increased. So the best examples for convey are chromium, nickel, and sulfuric acid. So in sulfuric acid, chromium, nickel, if I increase the temperature, the corrosion rates are increased. See, why I am saying is, take this example. Chromium, nickel, the best possible material in all equipments. You take any heat exchangers, you take any evaporators, you take any distillation columns, we use this material only. This material in sulfuric acid, because when you are in industry, there will be sulfuric acid will be produced. So if this metal is in this metal of construction, if sulfuric acid is preparing, if I just increase the temperature, the corrosion rates are increasing. So you should be very careful. In any industry, if acids are producing, you have to take utmost care because you see, all acids will try to increase the corrosion rates because all acids will act as oxidizing agents. All acids will peel off the electrons. All acids will increase the corrosion rates. Apart from that, if I increase the velocity, if I increase the temperature, much more corrosion rates. Bhopal gas tragedy we discussed. Methyl isocyanate leakage we discussed. Why that was happened? It was happened because of high temperatures and high pressures. It was leaked. The gas was leaked. So why it was leaked? The material of construction has not sustained. Why it has not sustained? The acids, oxidizing agents, were trying to scratch the surfaces. Fine. So what is case B? Case B is, see, if I increase the temperature, there will be passive, but after certain temperature, the oxide level is gone and then the corrosion rate will be more. The examples are chromium, nickel, and nitric acid. Understood? So this is effect of temperature. Fine. Effect of velocity. Effect of corrosive concentration. What is corrosive concentration? That means the concentration, the amount of corroding agents if I added, if I increase the concentrations, what could be the corrosion rates? See, the corrosion rates will always be increased if I increase the concentration. But after some time, even though I increase the concentration of the corrosive species, the corrosion rate will not be increased, it will decrease. Because after certain concentration, the ionization will stop. The ions formation will stop. So there won't be any corrosion. So that is for the case of B. Case B. But for cases like case A, initially if I increase the concentration of corrosion, there won't be any corrosion. Passive mode and then active mode. So curve A, section 1, section 2, section 1 and 2 for curve A. Look at here. 1, 2, monal in, in HCl, lead in sulfuric acid. So for every case, you just remember one example. See, I have given four or five types of examples. For one section, for one example, you remember just one. See, you remember one combination: 18 chromium, 8 nickel, and nitric acid. You remember the combination. Wherever it is quoted, you remember that. That's all. It's very easy. You understood the mechanism, you understood the concept. You remember one example. That's enough. Even you don't remember this example if you visit an industrial plant, because you with your eye you can see the material of construction, 18 chromium, 8 nickel, because I visited, I know the compositions, I know 316 stainless steel, I know 304, I know 306. How I know? Because I have visited. So that's why the industrial practical exposure is very important. Okay, fine. So any doubts? I have discussed four concepts: effect of corrosive concentration, effect of temperature, effect of velocity, and then effect of oxidizing agents. So two or three segment, each example I have discussed. Any doubts? Okay. So I'm stopping here. So I'll move to next concept in next class.